I even remembered to hit record all by myself on the last day. Okay, so let's talk about some schedule-y kind of stuff before we continue with chapter 22. So it is the last lecture of the semester. So we're going to finish chapter 22 today. Lab today is worksheet 22. So obviously you can do that when you would like, but that's what's officially on the schedule. And then chapter 21 worksheet is due today. Next week on Monday is a study day during lecture and lab practical time during lab. So I won't have any lectures planned or anything planned during those times. I will be on Zoom, and you are more than welcome to come hang out and work on stuff, study, ask questions, however you want to use that time, but I won't have anything official planned. Wednesday will be the test. I do have it written. I wrote it, or I typed it up in between my classes today. So after class today, I will type up the study guide and then get that posted tonight so you guys can have it. So if you want to start studying over the weekend. And so the test will be similar to what we've done, meaning Zoom during lecture time, all that. Then the following week, again, Monday is a study day, lab practical time, and then that Wednesday will be our final exam. So a couple things. In the morning class, somebody had asked if we were taking the final during lecture, and what I'm planning on doing is sending out a little survey to you guys. If we do it just limited to lecture time, it kind of limits us to just an hour for a test. But for a final exam that covers an entire year of organic chemistry, I'd like to give you guys some more time. So I'm thinking of starting it at the same time. So starting it when our lecture would start, but overlapping into what would be lab time. So because we have lecture and lab back to back, we have some wiggle room with how we want to do it. So I'll send out a little survey just to kind of see what people would like. I'll figure out some options to go with that though. And then one more thing about our test for next week. So it's 4 parts, which is what you guys have kind of gotten used to seeing. So there's nomenclature, which is just the amines. Box problems. Those are going to come from both chapters. So today we'll talk about all the reactions in chapter 22. Mechanisms, which are just chapter 21. You don't need to know any of the mechanisms from chapter 22. And then the last part, which is normally multi-step synthesis, I'm replacing it slightly in this chapter. Well, not slightly, I'm replacing it in this chapter. So normally we would do multi-step synthesis, but at the end of chapter 21, we have a handful of those reactions that are a little bit more intense. They are bigger starting materials, bigger products, multiple things kind of happening. They're kind of their own multi-step synthesis. So I'm doing the last section of the test as a retrosynthesis, meaning I will give you the product and I will tell you that it's a Michael reaction, or I will tell you that it's a Robinson reaction, and then you have to figure out the reactants and the reagent. And I will put that in the study guide as well, but your little heads up on that. Jared, that is a good question. I haven't written it yet. So normally we do a standardized test, American Chemical Society. But because we're online, we can't use the American Chemical Society test because we can't post them online. They have some very strict copyright rules, and if we post them online, we can easily get fined lots and lots of money, like $30,000. So we are not going to do that. So I have to write it myself. It will cover both semesters. You definitely don't need to know everything. I'll give you some guidance on kind of how to narrow things down. Yeah, that's all I got for you right now. So I will write it next week and get you some kind of study guide or some kind of guidance for it then. Less time on the final would mean a shorter test. True. So if we have less time for the final, it would mean a shorter test. But remember, the test is worth a lot of points. So that also means that it would be more points per question. So some people would, just in general, would want more questions on of a test that are worth less points each, so that if you miss one, it's less damage. Well, yes, you'll get a study guide. It will be similar to the rigor of the ACES. It's not, let's see, that's a hard question to ask, or answer. I mean, easy to ask, hard to answer. Will be similar to the rigor. It's not going to be similar to the ACS, and for a couple reasons. One of the things that makes an ACS test challenging is that they'll ask you a question, but to answer that question, you kind of have to answer like 4 like prerequisite questions to get to the answer. You have to know like lots of background information, which in all honesty is a great way to test knowledge over a year, but it's also really hard to write a test that way. And I don't have like a test bank of old questions to go from because I've always used an ACS test. So I don't have previous exams that I've kind of cleaned up over the years. So I think that mine will be more straightforward than what an ACS test would be. Difficulty wise, though, I don't know. It kind of just depends on where your strong suits are. I would expect it to be like the same difficulty level as my regular tests, because I'm just going to be writing a similar test just with both not both chapters, both semesters worth of stuff on it. Any other questions on that kind of stuff? Okay. And if you think of any as you're studying over the weekend for the upcoming test, or if you start thinking about the final, you can always text me or email me. Full MO theory. It's all it is. Let's do that and that. Do some adjustments over here. Okay. So we have almost covered this whole slide. Taking vigorous notes on the side. The only thing we actually haven't talked about on this slide is this very last one. And so it's looking at a benzene ring. So I'm going to actually draw three structures here. We're going to look at a benzene ring with a nitrogen group versus an amide, and then just a cyclohexane. And so what we were looking at on this slide on Monday was how basic our nitrogens are, so how good they are at grabbing onto a hydrogen. And when we have these three in comparison to each other, our cyclohexane is going to be the strongest base out of these three. And our reasoning for that is because the lone pair on both of these nitrogens is delocalized. So we've drawn these resonance structures. We've gone from a activating group on a benzene ring and then put those electrons onto the ring. And then we've also gone from our nitrogen up into a carbonyl. Out of these two, though, the benzene has more resonance contributors. And so this one is going to be the weakest base out of these three. And one way to think about this that I think I think helps kind of make it stick in your head, or even just make the most sense, is when we have those electrons. Wait, let me take one more step back. When we're doing the acid-base reaction, the base's job is to use its electrons to grab onto a hydrogen. When we have delocalized electrons, though, those electrons don't belong to the nitrogen. They are being rotated throughout the structure. When we have that benzene, it has lots of resonance contributors. It would, in this case, it would have 5 resonance contributors. With our amide, it's only going to have, I think, 2. I'm trying to figure out if there's a third one in there somewhere, but I think just 2 resonance contributors. So our lone pair is spending less time on just the nitrogen because it's able to be shared throughout the structure. The benzene one, it can share more than an amide can, so that means it's going to be the weakest of these bases. So kind of long story short is that if the lone pair on the nitrogen is delocalized, it's going to be worse at being a base. Okay. We're going to talk about some reactions. So there are 17, is that right? 17 reactions in this chapter. A handful of them, maybe about a third of them, we've already seen in past chapters. As I've mentioned a couple times, I'm going to say it again. You don't need to know any of these mechanisms for the test. We might talk about some of them, though, to help understand and see what's happening. So our first section is how to make amines, but notice right there in the title, it's telling us that it's a review section. So these are ones that we have seen in past chapters. So reaction number 1, we're starting with our alkyl halide. We're reacting it with a cyano group. So this is sodium cyanide, but we're really just doing an SN2 mechanism. That negatively charged carbon is our nucleophile. Our bromine leaves, we get our SN2 mechanism in there. And then in that second step, we're reacting it with excess lithium aluminum hydride and some water. So I think that was chapter 20, kind of guessing there, but I think it was in that chapter. And then that will reduce our carbon-nitrogen triple bond down to a single bond. One thing to make sure that we point out for this, though, is we are creating a primary amine, and we're adding a carbon. So when you're looking at reactants and products, this reaction will add 1 extra carbon to the chain. So it's not like that's a bad thing or something. It's just something that we need to make sure that we're aware of. So the cyano group carbon is part of that chain now. In this second reaction, now this one is really like 3 different reactions kind of mushed into one. So here's what I mean when I say that. We're starting with a carboxylic acid. And in the first step, we're reacting it with SOCl2 or thionyl chloride, but we know that that's going to make, let's try to fit this in here. Do a little bit lower. There we go. That's going to make an acid chloride. And then in the second step, we turn the acid chloride into an amide. And then in that last step, so this would be like step number 3, if we were, or 3 and 4, I guess, if we were stacking them all on top of each other. This is also from chapter 20, taking that amide, reacting it with excess lithium aluminum hydride, and again, we get that primary amine. Now, the reason I say that this is like multiple reactions kind of mushed together, because this is showing us how to make an amine starting with a carboxylic acid, an acid chloride, or an amide. And depending on which of those three we start with, we're just kind of like cutting some steps out. So if we're starting with an acid chloride, our first step would be to add the amine. And if we're starting with the amide, the first step would be to add the excess lithium aluminum hydride. So it's just kind of creating that little chain of reactions, and you kind of jump in with whatever starting material you have.
Hey, Professor.
Yeah.
For the first one, the substitution and reduction, where does the extra carbon come from?
It's the carbon from the cyano group. So it's this carbon right here. So when it adds onto the chain, if we go back and count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, the sixth carbon is the one that's part of that cyano group.
Okay, thank you.
Anything else on this, on those first couple? Okay, let's look at the third one then. And so this is going back to our benzene chapter. First step, nitric acid, sulfuric acid. This is to add the nitro group to the ring. So we don't have a way to directly add an amine to the ring, but we know how to get there. So we can start with that nitro group, and then we can reduce that nitro group down. And we have a couple different ways to do that. Hydrogen and a platinum catalyst. Or, and I don't think we had this full list when we talked about it back in chapter 17. I don't remember what chapter that was. So our options here, though, are some kind of metal. So we have iron, zinc, tin, or tin chloride. I think we just had iron and zinc in that earlier chapter. I'm not sure why our author gave us more in this chapter and less in the previous chapter. But one of our metals here with some acid and water. And then in the second step, we're doing a basic workup for that. So again, this is one that we've seen. It's in the back of your head somewhere. But all three of these, and this one is also primary, all three of these are making primary amines. Questions about any of those three? Okay. Number 4. Number 4 is kind of a horrible reaction. We're going to make it useful, though, in a couple reactions, in a couple slides. So number 4 is alkylation. So essentially this is saying you have a nitrogen and you want to add carbon groups to it. The reason why I say this is a horrible reaction is because of the second bullet point right here. We can't stop at the monoalkylation. So whether we're starting with ammonia, a primary amine, a secondary amine, or a tertiary amine, we will end up with a quaternary ammonium salt. So a nitrogen with 4 R groups attached to it with a positive charge. The reaction, I'm going to write it out here in a little bit more general terms. We're starting with an amine, and again, it could be any of those forms. I'm going to write it out as ammonia. And in this, we're reacting it with an alkyl halide. So the specific alkyl halide that's used here is methyl iodide. And then what we end up with is 4 of those groups attached to our nitrogen. And the halide is just our counter ion because we've created a salt. So remember, salt's just another word for ionic compound. But because we've added that 4th group onto the nitrogen, it's now a cation. And so the anion from the alkyl halide is going to stick around to balance out that charge. The reaction itself, we start with an SN2. So our nitrogen acts as a nucleophile and our halogen is our leaving group. And then a second nitrogen molecule is going to remove the hydrogen. So we do a proton transfer to remove the hydrogen off of that first nitrogen group. And that process just continually repeats until there aren't any more hydrogens on that nitrogen. So, not a good reaction because we don't have much control over it. But as I said, we will look at it on a couple slides from now on how this can be put to use.
Professor?
Yeah.
About that reaction, and I don't know if it's specific to this reaction, but I noticed that the iodine is being used, or the iodide. Isn't that typically like pretty slow to react? How come it goes all the way through to complete alkylation if it's so slow?
It goes all the way through because the nitrogen is a really good nucleophile. So it's slow to react because it's not the best leaving group out of our halogen options. But because our nitrogen is such a strong nucleophile, it is able to complete the full series of reactions, I guess would be a way to put it. And we also are using iodine because it's large. And so we want to have that larger anion to pair up with what ends up being a large cation so that their sizes are more comparable with each other.
So the iodine is more for counteracting the large cation that forms from.
Yeah, at the very end. Yeah, throughout the actual reaction, the fact that it's iodine doesn't play a huge role.
But since it's slow, would you not be able to, like, I don't know, like pull it out before, or no?
So to like prevent it from going all the way through, you mean?
Yeah, if it's slower than the
So
small
there's
legs.
you can't and the reason why isn't because it would stop it from reacting. It's because not all the nitrogens are reacting at the same speed. So remember, like way back in like general chemistry, and one of the things we talk about is when molecules react, they have to run into each other in the right way. So they can't just like hit each other however they want. Um, that means that a nitrogen that's in the solution might react immediately because it runs into the methyl group, but another nitrogen might take some time to get in the correct orientation. So if we try to remove the excess methyl iodide, or maybe even just put in less of it to start with, some of the nitrogens might reach like a secondary amine. Some of them might get all the way to the quaternary. You just kind of would get like a mixture of what has been able to react at each level. So you could prevent some of them, but then others will have reacted all the way. So it's not controllable enough.
Okay, that makes sense. Thank you.
I don't know if controllable is a word, but it works. Any other, before I switch slides again, any other questions on that? Okay. So because this isn't the best way to make an amine with things attached to it, we do have other ways to do it. So this is our next way. This is using an azide. So this is number 5. This is the azide right here. So we're using sodium azide. And we're going to see that word pop up a couple times in this chapter. An azide is 3 nitrogens double bonded to each other. The 2 nitrogens on the end have negative charges, and the nitrogen in the middle has a positive charge. So we're starting with our alkyl halide. And the reaction that's happening here is an SN2. So this is going to work best with a primary or a methyl alkyl group. We react it with the sodium azide. So down here in the bottom half of this slide is our mechanism. That negatively charged nitrogen is a good nucleophile. So we do nucleophilic attack, we do loss of a leaving group, SN2. In the second step of the reaction, we're going to do a reduction. We're going to reduce that nitrogen group down. We have a couple options: hydrogen with platinum or lithium aluminum hydride and water. The mechanism that's shown is with lithium aluminum hydride. So we've talked about this before, but when we're using like a metal catalyst that is part of the reaction, like the hydrogen with the platinum, we don't really look at their mechanisms. It definitely falls into that inorganic category, and it just doesn't quite match our patterns. So when we use the lithium aluminum hydride, we're going to start by using the hydrogen as our nucleophile. And so we're going to bond to that nitrogen, and then we just kind of shift those electrons over. This is our intermediate. The electrons that are moving here are, the driving force is that negative charge on that nitrogen. It's labeled as the loss of a leaving group. The leaving group, though, is actually the part that we care about. So what defines a leaving group is that when a bond breaks, whoever takes the electrons is the leaving group. So normally we think about it as like a halogen, like in the first step here. When that bond breaks, we put the electrons onto the halogen. The halogen was our leaving group. But in this molecule, the bond that's breaking is this single bond right here between those two nitrogens, and we're putting the electrons onto the nitrogen that has the R group. So that is our leaving group. It's the part that we care about. At the same time, the lone pair from the terminal nitrogen is going onto that double bond to create a triple bond. So that becomes N2 gas. And this is a good thing. We know that when a gas forms as a product, it just bubbles away. We don't have to worry about it. We don't have to worry about separating it, but also we're removing a product. And so based off Le Chatelier's principle, we know that that's going to push the reaction forward. So we end up with a negatively charged nitrogen. And so then that last step, that water that we add in, is there to just do a proton transfer to make our nitrogen back to being neutral. So this is also making a primary amine. So a little bit of a trend with all of our useful reactions just making primary amines. We're gonna switch that though. We're gonna make sure that we have a way to make secondary and tertiary amines as well. Any questions on this azide one? Number 6. Number 6 is called the Gabriel synthesis. And I kind of feel like the Gabriel synthesis is in the same category as the malonic ester synthesis and the acetoacetic ester synthesis. And what I mean by that is we have very strict things that have to be used. And the only thing we have control over is what alkyl halide we're going to start with. So the chemical that we're using here, this big thing, is called phthalimide. So I'm going to draw out kind of the generic version of this reaction. So again, we're starting with phthalimide. That's not an option. This reaction just always starts with that. First step, we're reacting it with KOH. We're reacting it with a strong base. That strong base's job is going to be to take the hydrogen off of that nitrogen. So we're doing a proton transfer. Second step, alkyl halide. Now this is an SN2 mechanism. The mechanism is shown right here, that nitrogen does a nucleophilic attack, leaving group leaves. Because it's an SN2 mechanism, this R, this alkyl group, methyl, primary. Secondary is okay. It's not great, but it's okay. It will do the job. No tertiary though. And then the third step is acid and water. What we make is that. So if we look at what we end up with on the very bottom of this slide down here, so this last step, made my line a little short there. Let's try that again. There we go, that last step. The phthalimide is essentially two amides kind of put together. It's almost like an acid anhydride, but with a nitrogen in between the carbonyls. And so when we react that with acid and water, the oxygen is going to do a nucleophilic attack on each carbonyl. We get our tetrahedral intermediate, and then the nitrogen group is going to leave. Yeah, there's a bunch of proton transfers in there as well because it's acid catalyzed. But we essentially are turning the amides into carboxylic acids. And that nitrogen leaving group gets kicked off, and we can make our amine from that. So up here, this is our kind of shortened generic version of it, but we're able to create an amine from that phthalimide that we're starting with.
How hard is phthalimide to make and have?
I don't know how hard it is to make, but it's really easy to buy. Because it has so much resonance and stabilization, it's a chemical that can be easily purchased. So it does look like kind of a crazy reaction just to make an amine. But it's I was going to say cheap, but I actually don't know if it's cheap or not. It is an easy chemical to acquire.
Huh, interesting.
Any other questions on this one? That carbonyl be more electrophilic than the hydronium. Be more electrophilic. The carboxylic acids that we made, is that what you mean? That carbonyl? The step before that. Excuse me. So the hydronium's not going to be electrophilic. So it does have a hydrogen on there. It does have a positive charge, but that oxygen, the hydrogen, okay, let me start that over. I'm sorry. Hydronium has that extra hydrogen on there because it is acidic. We can use that hydrogen to protonate the carbonyl. So it will actually be in the form of water before it does the nucleophilic attack. And then that oxygen will be our nucleophile to attack that electrophile carbonyl. So even though it's positively charged, the oxygen of hydronium is still going to be a nucleophile because of its lone pair. It just has to get rid of that hydrogen first as an acid catalyst. Does that make sense, Nilla? Does that answer your question? Okay. Yeah, and I kind of drew, well, I really drew a half-assed mechanism there because there's a lot of other proton transfers that are happening before that step that I drew. Matt does come in with the good facts. Anything else on this one? Okay. So this one might be the most useful because we can make a primary, secondary, or tertiary amine. So it's called a reductive amination. We have kind of done this reaction before. So back in our ketone aldehyde chapter, we added ammonia, primary amine, and secondary amines to our ketones and aldehydes to make imines and enamines. And then we also learned how to take those enamines and reduce them back to their ketone form, or turn them back into their ketone form. We're kind of doing that in this one, but we're using a more selective reactant. So let me explain what all that means. We're starting with our ketone. Technically, you could do this with an aldehyde as well. So ketone or aldehyde. And then we're reacting it with either ammonia, a primary amine, or a secondary amine. No tertiary amines, because it has to have a hydrogen that can be removed. A catalytic amount of acid. So that's, I think we've talked about this before, but when we have the brackets around there, it means it's a catalytic amount, which really just means it's not in a 1-to-1 ratio. It's a smaller amount. And then when we did this before and we wanted to get back to the ketone or the aldehyde, we could use sodium borohydride or lithium aluminum hydride. But what we're using here, this guy, is sodium cyanoborohydride. When we used lithium aluminum hydride in our carboxylic acid derivative chapter, it would take one of our carboxylic acid derivatives and turn it all the way down to an alcohol. But if we wanted to go from one of our derivatives and stop it at the aldehyde, we had lithium aluminum hydride, but we would replace the hydrogens with something bigger and bulkier. So we had a tert-butyl oxide group. This is the same idea. We've replaced one of the hydrogens on our borohydride with this cyano group. It makes it bulkier, which makes it less reactive, which makes it more selective. So it allows that amine to stay on the structure, but we're removing any of the double bonds that have occurred. So as a result, we can turn our ketone into an amine, primary, secondary, or tertiary. So let me just add a little note here. So this compound is less reactive, which means more selective. And I'm comparing that to just NaBH4, sodium borohydride, when I'm using those terms. Any questions about this one? Okay. This is one we also know, and it's actually kind of one we talked about already. We know how to make an amide, which is essentially what's being shown here. But we're kind of showing it for a specific purpose. So number 8 is making an amide. Amine, acyl chloride, we get an amide. The reason why it's being shown here, though, is for 2 reasons. One, it can be used as a protecting group. So we've seen this with ethers. It's kind of the same idea. We're attaching it on to turn our amine into something else, but that is still similar, and then it can be removed back off. And then the second thing, which is what the picture on the bottom is for, is changing the reactivity of benzene. So there's a couple things here. Our amine is a strong activating group, and it's pretty small. It's about the size of a methyl group. But an amide is a moderate activating group, and it's a lot larger. So in this specific example, the bromine is going to add para to our amine after it's turned into an amide because of the steric hindrance of that amide group. If it was just in the amine form, though, it would add ortho. The other thing is, and this was one of those small little detail rules that we talked about at the end of that chapter. We can't add we can't do a Friedel-Crafts reaction if we have a moderate activator on the ring. And so this, or I'm sorry, I said that wrong. Let me reword that. We can't do Friedel-Crafts if there's an amine on the ring. So no Friedel-Crafts with amines. This was just one of those very specific rules. The amine will react with our aluminum chloride as opposed to using the aluminum chloride as a catalyst. So not really a big deal about why it can't react at this point, but it can't happen. We can't do the Friedel-Crafts reactions if there's an amine on the ring, but we can do the Friedel-Crafts reactions if there is an amide on the ring. So essentially this is kind of a protecting group. We're protecting that nitrogen from the other reagents. We add on an alkyl or an acyl group, and then we can turn that amide back into an amine at the end of the Friedel-Crafts reaction. So I don't think we ever got quite that specific in our benzene chapter, but we definitely kind of touched around the edges of all that. Questions about that at all? Okay. So the first new reaction I said was kind of a useless reaction. Here's where we actually put it to use. Reaction number 9 is called the Hoffman elimination reaction. And what we're starting with is our amine. And it can be a primary, secondary, or tertiary amine. It doesn't matter. Oops. Can't be methyl, can't be quaternary, but primary, secondary, or tertiary would all work. We're going to react it with excess methyl iodide. So this first step is actually, looking back at my notes to see what number it was, reaction number 4. So what we get after we do that step is our nitrogen with 3 methyl groups attached to it and a positive charge. We do that because it turns the nitrogen into a good leaving group. Nitrogens are normally really poor leaving groups, but when they are fully alkylated and they have that positive charge, it's now a good leaving group. So the second step is silver oxide and water. In solution, these two become hydroxide. I mean, obviously there's other stuff in there. There's still silver in there, but they're going to create hydroxide in solution. And then, of course, there's some heat in there. But what we end up doing is we do an elimination. So that hydroxide that is created is going to remove a hydrogen off of one of the neighbor carbons. The electrons form the double bond, and our nitrogen becomes the leaving group. So it's essentially an E2 mechanism. What we get is the Hoffman product. So remember way back when, and I see I have Hoffman spelled 2 different ways on here. I think it's with 2 F's. I don't really know though. That's a guess. I'm looking to see if I wrote it in my notes. No, don't even have the name in my notes. Back when we talked about SN1, SN2, E1, E2, when we talked about elimination products, there was the Zaitsev product and the Hoffman product. The Hoffman product is when we form the double bond on the less substituted side. So this will be our major product for this reaction. So are you referring to the 60% thing, Justin? So the 60% isn't saying that 60% is Hoffman and 40% is Zaitsev. It's actually saying that that's what the percent yield is. So it's saying that it's, believe it or not, it's kind of bragging about the percent yield, because 60% yield is actually a decent yield for organic chemistry. So it's saying that we can form this alkene with decent yields. When we talked about Hoffman versus Zaitsev, oh yeah, I'll draw out the Zaitsev too. When we talked about Hoffman versus Zaitsev, it was pretty difficult to create a Hoffman product. So this is a decent way to do it. Our Zaitsev product for this, so our minor product, would be with the double bond on this side. So the Zaitsev is when our elimination goes to the, whoops, more substituted side. Of course it is. I'm just going to spell it all the ways then. Thank you, Natasha. It just seems to go with 2020 that Hoffman would be spelled that way. So this allows us to make that less substituted alkene. The Zaitsev is the minor. Oh, the reason there's somewhere my brain was going. The reason why we get the Hoffman is because that nitrogen group is so bulky. We've attached 3 alkyl groups to it that our base, when it comes in to remove that hydrogen, wants to go to the side without anything in the way. So if we think about how it would approach either one of these sides, this right-hand side just has a lot more availability, a lot less steric hindrance. Yeah, exactly. So this is doing the exact same thing that first reaction is doing. It's fully alkylating. It's just we've now done that with a purpose. We've done it so that it can be a leaving group. Any other questions on this one? Okay. Number 10. So these next 2 reactions, number 10 and number 11, are very specific. The title of the section, Reactions of Amines with Nitrous Acid. Number 10 is with secondary amines. So here's our secondary amine. Nitrous acid is very unstable, and so we don't react it with it directly. Instead, we use sodium nitrite. And a strong acid. So it doesn't have to be HCl, it just needs to be a strong acid. But then in solution, nitrous acid will form. And then what we get is called a nitrous amine. So we still have, let me get some colors, other colors in here. Our nitrogen with the 2 R groups, and then the nitrogen from the nitrous acid have kind of combined together. And I have never really seen this reaction used. I always see it in textbooks, but in all of my years of teaching and my years of doing research, I've never actually seen this reaction put to use. So take that for what it's worth. I don't know how helpful of a reaction it actually is. I'm sure it's one of those reactions that some people do all the time, but it just has a very specific use to it. With that being said, though, the one for a primary amine and nitrous acid is useful. So here's our primary amine version of the same reaction. Yeah, it kind of is. It breaks down very quickly. And so just like carbonic acid, it gets formed within the solution, but it's in equilibrium with its like deep with its ionized form. So yeah, it is kind of almost imaginary. When we react that same combination of chemicals, so sodium nitrite, a strong acid, but we're reacting them with a primary amine this time, we make a diazonium salt. So we have, and so notice we have that word or that suffix in there, azo. So kind of like an azide. We have that nitrogen triple bond in this one. It is a salt because the nitrogen has a positive charge. So the anion that we have is whatever was on the strong acid. So if we were using HBr instead, this would be a bromide ion. There's one specific example of this, though, I want to draw out. So we do have it drawn very generically, just with an R group. But if that R group is a benzene ring, and we can make, I'm even going to draw this kind of cheat version, just writing the N2 there. The common way to write this out. It's the same reaction. We're making a diazonium salt. It just happens to be that our R group is a benzene ring. But this leads us into a bunch of reactions we're going to see on the next couple slides, where we have created this azo group attached to our benzene ring, which is actually a really good leaving group. So remember in our benzene chapter, we learned how to add like, I don't know, 5 things to the benzene ring. And then we talked about a couple different ways to do substitutions, but the settings were pretty specific and the conditions were pretty harsh. So this is essentially like an alternative to some of those substitution reactions. So here's the first set. So this is reaction number 12. They are called the Sandmeyer reactions. So we are starting with that diazonium salt attached to our benzene ring. And notice what we're reacting it with. It's a copper cation bonded to a nucleophile. I'm going to write that underneath because that looks weird. So copper cation and our nucleophile. And the nucleophiles that we're using for this, bromine, chlorine, iodine, cyano. So we do have other ways to add bromines and chlorines onto the ring, but we haven't had a way to add iodine or cyano directly onto the ring. So this does give some alternatives for things we already know, but also some new substituents that could be attached to the ring. Questions about those? Okay. So 13 and 14. 13 is the Shineman reaction. So this is a way to put a fluorine on that ring. HBF4 is called Fluoroboric Acid. So again, it's a type of substitution reaction. We're losing that N2 group, replacing it with a fluorine. And then in the last two, we have water and heat to create phenol to replace it with an alcohol group. And then in the last one, we're using hypophosphorus acid. And this just completely removes that N2 group. And so we just go back to having just a benzene ring there. Questions about any of those? Oh, sorry. I didn't mean to click quite yet. Okay. So last one in this kind of azo grouping is called an Azo Coupling reaction. So we're starting with our Diazonium Salt, our aryl diazonium salt. We're reacting it with a benzene ring with an activator, an activating group. What we create is a bond between the terminal nitrogen and the new benzene ring. So a couple things to point out. First thing is that the bond between the nitrogens was a triple bond. Now it is a trans double bond. Second thing to point out, the new bond between the nitrogen and the benzene ring is going to be para to the activating group that was already on the ring. So we already know an activating group is an ortho-para director, and what we're adding onto the ring is pretty bulky. So para makes sense from what we know from our benzene chapter. You don't have to go back and rememorize your activating groups. We can just kind of do the shorthand version of this and think of it as just a heteroatom with a lone pair. I know that doesn't include everybody, but it's definitely a good summary of probably 80% of our activating groups fall into that category. So as long as the heteroatom is directly attached to the ring and it has an available lone pair. This product that we're making is used as a dye. So the colors that you're seeing in Beyond Labs are correct. And if you were to do this, not this lab, if you were to do our class's lab in person, you would see that we make a lot of clear colorless oils and white powders. Organic chemistry is not something that people get into because it makes pretty stuff usually. Inorganic chemistry makes a lot of pretty stuff. Metals make things colorful and pretty. Organic molecules that are colorful, though, are colorful because they have a lot of conjugated double bonds. We talked about this when we learned about UV vis spectroscopy, and I talked about lycopene makes tomatoes red and beta carotene makes carrots orange. They have a big string of conjugated double bonds. When we connect these two benzene rings together with a nitrogen-nitrogen double bond, we now have a very long conjugated system with all of those double bonds, and these are colorful. So it is actually an Azo dye, and it can be used to dye fabrics. And it is a way to, and I don't actually think that these dyes are like manufactured and made anymore. I remember reading about this a few years back. I honestly don't remember why. It's somewhere in the back of my brain. But they, at one point in time, they were manufactured and made as dyes for fabric. So, and they are fairly colorful, and you can change what color they are based off of what's attached to the ring, and if what's attached to the ring has even more double bonds on it. All right, last two reactions. Number 16. So number 16 and 17 don't quite fit into this chapter. And I say that because it's not the nitrogen that's reacting. We're reacting what are called nitrogen heterocycles. So cycle means it's a ring. Hetero means there's a non-carbon present. And so this means that we have a ring that has a nitrogen in the middle of the ring. So specifically on this one, we're looking at Pyrol, which is this guy. Sometimes these reactions are in the benzene chapter because the two chemicals we're going to look at are both aromatic. So they're just kind of lumped into like aromatic reactions. But in this reaction, we're reacting Pyrol with Br2 under cold temperatures, so 0 degrees Celsius, and the bromine is going to add to the number 2 position. So I'm going to show you where that number is coming from. When we have that hetero atom in there, it becomes carbon number 1. So 2, 3, 4, 5. So the bromine will add to carbon number 2. This has to do with resonance. So that lone pair that's on the nitrogen can participate in the resonance of this structure. It's delocalized. So we have this resonance here. We don't want that double bond to end up at the same position as the bromine. So putting it on carbon number 2 will prevent that. So it's very similar to what we talked about in our benzene chapter, where as we move electrons around the ring, we want them to hit in certain spots, but not in others. So same idea. I feel like there was something else I was going to say. Should we know? No, you do not need to know the mechanism. Again, it's just to kind of show you what's happening, but it's not one you need to know. Oh, I remember what I was going to say. So we are looking at this with bromine. It's the only reagent that our book talks about for Pyrol, but there's a lot more. There's a lot of other things that we can attach to a Pyrol ring. We're going to keep it to what our book is talking about, meaning this is it. I'm just bringing it up so that if you are watching other videos or looking online for other resources, you will most likely see other reagents or other substituents that can be added to this ring. We're not going to get into the other ones though. All right, and the other heterocycle is pyridine. And so we've used pyridine as a reagent in a couple reactions. It works as a good base. This is pyridine, but we're doing the same thing. Bromine. This time though, we need some hot conditions, so 300 degrees Celsius, and we're going to add our bromine. Oh no, I thought I skipped a carbon there for a second. We're going to add our bromine to carbon number 3. And this is for the same reasons as we do the resonance. We don't want that positive charge to end up on carbon number 3. We want to have that atom skipped as we go through and move our electrons around the ring. So the resonance will stabilize our intermediate better if we're adding it to position number 3. And then same thing with this one. If you look pyridine reactions up online, you're going to see a lot more substituents and a lot more reagents, but we are limiting it to what our book talks about, which means we're limiting it to the bromine. Questions about either of the heterocycle reactions? Okay, that's it. This is our last slide. We are done. So I will get our study guide for this test up today. As soon as we're done, I will get it posted. Well, that's not true. As soon as we're done, I will get to typing it and then get it posted. But that's it. So thank you guys. I will see you next week. Feel free to hang out if you have questions for me as we're logging off, but that's it for today. I know, it is kind of an underwhelming chapter. It's a weird one to end with. That's kind of how it happens, though. A lot of times they'll do like, there was one book I referred to it as the kitchen sink chapter because it was just kind of like all these like little things thrown together. You are very welcome. Thank you too. You are welcome.
Professor,
Yes.
about those what are they called? The student tutors.
Oh yeah, yeah. Yeah. SI?
SI, that's what it is. Goodness gracious.
I know.
I,
Yeah.
I feel so silly. I mean, I'm a bad student. I haven't been to a single SI session. But I'm doing all right in the class, I suppose. Would those be specifically for your class, or is it just for the organic chemistry department in general?
So I know that they are hiring specifically for organic chemistry. I don't know if there is a need for the lower level classes or not. And so on that flyer that was attached to the announcement, let me see if I have it. I think I have it saved on my desktop. It had the schedule on there because a big part of finding SI leaders is, oh, I don't think I do, is finding people that will fit with the schedules, because the SI leaders are supposed to attend all the lectures, and then ideally they like to have the SI session right before the lecture. That doesn't always happen. That definitely didn't happen this semester for us. But that's what they want. And so on that flyer, it has the schedule for all of the organic chemistry classes. And I think they even put like when they would want the SI sessions to be. So part of it is my class.
Well organized.
Yeah. Professor Torneo is the one that's in charge of it. She's the SI coordinator, I think is her title. But yeah, she's really good about it. And so if you were interested in doing like general chemistry or intro chemistry, you could always email me and let me know, or email her directly and see if there's an opening in another class.
No, it'd be interesting to keep fresh organic chemistry. I'm just curious because currently I work as a student tutor in MASH lab as a math tutor. And I told myself that I would be able to keep up all my math knowledge, and that has been proven to be woefully incorrect, as I have forgotten just about everything that was ever told to me about linear algebra or differential equations.
Yeah, and that goes away fast.
So with you might be lucky for me to be able to help you with some things up to Calc 2, but beyond that, man, there's a lot of things that if you do not keep practicing them, then
no, mine is long gone. I remember having a student like early in my teaching career ask me if I would help them with their calculus homework. I was like, yeah, sure, why not? And thinking I had it all in my brain still. And as soon as I looked at it, I was like, oh, I'm sorry, I don't remember any of this. I couldn't even like fake my way through it.
No, for me it just becomes like a game of hold on as I type something in real quick.
Yeah.
And I essentially just hope that I can figure out their notes fast enough to be like, all right, here, let me teach it to you in a different way.
Yeah.
But no, so that being said, while organic chemistry is still fresher in my mind, since chemistry is going to be more integral to my degree anyway, it sounds like an interesting opportunity to be able to continue doing that.
Yeah, it really is. The college I went to, we didn't have like an SI program, but I was a TA for a lab class. So our lab classes, it was like 90 students were in one lab class, and we met in like a lecture room to hear the pre-lab lecture, and then the class broke up into 3 different lab rooms. And so there was one professor, but then each class had an undergraduate TA. And so I started TAing general chemistry classes when I was an organic chemistry student, and going back and like rereading the labs and reading my own lab notebook after the fact, I was like, oh, that's why we did that. And it actually made sense after the fact, as opposed to just like following all the little steps. So it definitely helps to see it a second time, explain it to somebody else. It cements that knowledge in a little bit better.
Yeah. So no, tutoring in Chem 280A, at least. Chem 280B, I don't know if I would, if I'm confident enough. I'm doing well enough this semester, but it feels daunting to me to be able to say, oh, I did well in the class, so that means that I can definitely teach you guys about it. But I mean,
yeah, if you're interested in doing it, I would love to have you. And yeah, and 280A is what I'm teaching next semester. So yeah.
Heck yeah. All right. Do I feel bad for my math supervisor who has been very kind to me?
Well, you can feel bad and still move on, though.
Yeah, absolutely. Thank goodness I haven't been one of the pet projects to transform someone into a math major.
Oh, gosh.
I've skirted under that radar.
Yeah.
All right, Professor, thank you for all of the lectures. I guess I won't be able to speak much during the night. Well, I can stop by, so I'll probably have questions. Yeah. But thank you for everything.
You're very welcome. Good.
Hey, Professor. I had a question about the SI2.
Oh, okay.
Yeah, I was interested in becoming one. Just because, you know, my next semester is my last semester, so I mean, I was kind of, and same thing that Justin said. I want to keep my memory of this class specifically.
Yeah.
So are you teaching 280B at all, or no?
Not next semester. No, I'm doing 280A. Let me see. I'm gonna pull up the flyer she sent because I don't remember who's teaching it.
Okay, because funny enough, I'm the opposite of Justin. I prefer this class much more than the first one, just because all that stereochemistry always kind of confused me. So I wouldn't want to.
Oh yeah, and that does feel like it's such a big part of
oh,
that.
Definitely.
Let's see.
Do you know how?
Oh, go ahead.
Oh no, go ahead.
I was gonna say, you said next semester is your last semester here?
Yeah. So
where are you transferring to?
I did more of a UC path. So basically all the UCs just wanted. It's weird because the CSUs, they're kind of weird. They're like, oh, take 1 year of calculus and then like 2 semesters of physics, and then just take like 3 random bio classes for some reason, and that didn't really mesh with me. So a lot of the UCs were like, just take physics, math, and chemistry. That's it. You don't have to take bio. So I prefer that. So, you know, the schools around here, Santa Cruz, Santa Barbara, UCI, Riverside, you know.
Nice.
I want to get into Berkeley, but that's kind of a hard school to get into, specifically because Berkeley has a college of chemistry. That'd be cool.
It is a hard one to get into. It's obviously a very good school, though, so it's definitely worth trying. I have, I think, 2 past students that are there right now.
Do you know UCI has a nuclear reactor?
I do, yeah. It runs underneath the freeway.
Yeah, that would be cool to work with.
It would be super cool. Okay, here is the schedule. So B is Professor Nala and Alex. I don't know if you know who Alex is. He worked in the Star Center for quite a while.
Yeah, he has a beard, I think.
He actually shaved it off this year, but yeah, really? Yeah, he shaved it off and cut his hair short.
Wow, he probably looks completely different.
Oh, he looks like, I mean, not that he's old by any means. I'm sure he's like half my age, but he looks like 20 years younger than he appeared to look.
Oh, wow.
So yeah, so here, this is up on Canvas. It's attached to the announcement. But this is the class time. And so you would attend the Zoom class. And yeah, it's all still Zoom next semester. And then this is their proposed time of when they would want the SI sessions to be. If the teacher like kind of pushes to have a certain person as their SI leader, but they can't make those times, then there is a little bit of wiggle room. But I know that they really do like to keep those times. Yeah, so you do have Oh, and she has two different. Oh, I don't think that this is completely correct because for Professor Nala, it only has one lecture time, but it has two different sections listed. So there might actually be more than one there.
I was actually thinking of the Professor Knowledge because that kind of works with my schedule. I mean, I have this feeling that no one's going to come into the SI session at 7 a.m., but we'll see.
And I know, like, I think things like that work well when we're in person, because if people are coming to campus, then they can, go to that before they go to class. But I think with Zoom, like having them at different times works just as well. So I don't know. Have you gone to our SI sessions at all?
I have not. That was one of the questions I have, just because I don't know, like I just kind of, it works better for me to just kind of cram everything in and work it out myself.
Yeah, I understand. Well, and I haven't talked to our SI leaders about their attendance, so I actually have no idea how the SI Zoom sessions have gone this semester. I've kind of left them do their thing.
Yeah, I mean, I'm pretty sure they're pretty good about it because I get like an email like every 2 days or every few days about the SI, and I'm like, I get it. So
they're trying the guilt trip method.
It feels like that. Sometimes I feel guilty for not going, but then I bet they're also relieved that they can just like, sit around for a little bit and then get paid.
Yeah, I understand that. I put myself through college by working at gas stations, and I worked a lot of closing shifts, and so I would, especially in grad school, I would sit there and do my like advanced organic chemistry reactions homework while I was selling gas and cigarettes. But it was nice on slow nights because I could just get through.
That doesn't sound that bad. Just get paid to study, basically.
Yeah, it wasn't bad at all, and we closed at like midnight, and so I'd close up and restock, count the register, and head home.
Yeah, that's kind of what I'm hoping that this would be, because like I love chemistry, and I like teaching because or I mean, as much as I can teach, because I think I've been teaching, I don't know, at least like 5 or 6 people, like, let's see, pre-calc, calc 1, 2, and then chem A, B, and this class, or chem 280A, just because I like to help people. So
nice.
I just take time out of my day and just, do it. So it's kind of a best of both worlds kind of thing. Like I get paid for it, and, I get to help people. So
yeah. And I mean, hey, I do it for a living, so I understand. I like doing it too.
yeah. And I get what teachers say when they like standing up in front of the, the whiteboard and actually drawing out the things. I miss that. It's hard to.
Yeah, I know.
They'll call me like during FaceTime, like with FaceTime, and it's hard to really teach that well. So I understand your pain.
Yeah, it's been a weird adjustment. Yeah, I will be happy to be in front of my whiteboard again for sure.
Yeah, me too. So these are just did they just send out this listing to organic chemistry students, or was this just kind of like for like, is there any other openings, or is it just specific to our classes we're taking right now?
I don't know if there's any other openings. I will ask Professor Torneo, since you guys would technically be qualified to do any of the classes. But this one was specifically sent to the people that are teaching organic chemistry right now to recruit for organic chemistry SI leaders for future semesters, or for next semester specifically. So I know that it was sent to just the couple of us that are teaching organic chemistry right now, because of course those are the ones that are hardest to find SI leaders for, because most of the time if people take organic chemistry, then they're transferring and leaving and going somewhere else. So it's harder to find, the people that are still on campus.
Yeah, because I'll teach 100A. I don't know about B. I don't really, that class is a little weird. There's a lot of math, and I mean, I like math, but that's
all that class is math.
Yeah, it's not fun math either. It's like busy math. So
It is busy math. That is completely true.
I can deal with the other one. So should I email her or 'cause
Yeah,
it's-
you are more than welcome to. Yeah.
Okay, because Tornado's the head of the SI, right?
Yeah. She's like, I think her title's like SI coordinator or something, but yeah, she's the head of the SI.
Okay. Then yeah, I'll do that because I'm interested in this kind of stuff.
Good.
I'll do that then.
Okay, perfect.
Thank you for all these lectures, Professor. I've enjoyed every single one.
You are very welcome. I'm glad to hear that.
Yes, my favorite class this semester.
Good.
All right. Then I guess I'll be seeing you.
Okay, have a good Thanksgiving.
You too, Professor.
Okay,
Bye.
bye.